This video focuses on solving exponential and logarithmic equations, and we'll answer the essential question: how do you solve exponential and logarithmic equations, with an emphasis on exponential equations for this video. To begin with, let's discuss the inverse operations that are used in solving equations. We know with a simple algebraic equation, let's say x minus 3 equals 10, we know that we can undo the x minus 3 to get the x by itself by adding 3 to both sides. So we use addition on both sides of this equation to solve for the x and get the x by itself, x equals 13. So in vice versa, addition can be used. In this case, subtraction can also be used if the equation were, say, x plus 3 equal to 10. And addition and subtraction are inverse operations. Likewise, multiplication and division are inverse operations. If we have 3x equals 14, we know that we can solve that equation, and we can undo or cancel out the division by 3 here, cancel out the multiplication by 3 rather, using division by 3. And if we divide both sides, the 3 divided by 3 will cancel out, and x will equal 14 thirds will be our solution. And again, vice versa, if the original equation involved division, we could use multiplication to undo that and solve. And we also have inverse operations with powers and roots. If we have x cubed or equal to 50, let's say, we know that we could solve for x and undo the cube by using the cube root and cube rooting both sides. The cube rooting undoes the cubing, and the x would then be solved by itself, and the answer would be the cube root of 50. And again, vice versa, if we had a cube root in our original, we could use powers to undo the cube root. And then when it comes to solving an exponential or a logarithmic equation, those two operations will undo each other. And in this case, in this video, we're going to focus on undoing an exponential function by taking the logarithm of both sides. For instance, if we have an exponential equation e to the x power equal to 5, the way that we're going to solve to get the variable x so that it's no longer in the exponent of the power e to the x is that we're going to take the natural log of the left side. We'll also take the natural log of the right side, and if we apply the powers of our logarithms, we know that an exponent, in this case x, can come to the front of the natural log, and we're left with x times the natural log of e equal to the natural log of 5. The natural log of e is convenient. We know that the base of the logarithm is e, and that matches what we're taking the logarithm of. So this turns into just 1. X times 1 is equal to the natural log of 5, or just x equals the natural log of 5. That's the solution to this exponential equation, which we solved by taking the logarithm of both sides. Another example would be something like 5 raised to the 2x power equal to 10. And again, we've got an exponential, and to undo the exponential, in other words, to get the variable out of the exponent, I'm going to choose to use the common log on this in this problem. Take the common log of the left side, the common log of the right side. If you haven't picked up on it, I chose the natural log in this first example because I knew this problem involved e, so I chose the natural log. In this problem I saw that there was a 10, and so I chose to use the common log in deciding which base to use in my logarithm. Again, the exponent 2x, this exponent here, can come out to the front, 2x times the log, common log of 5, and that's going to equal, I know the common log of 10 is just 1, so that simplifies my equation a little bit. One last step to get the x by itself is to divide both sides by 2 log 5. 2 log 5. The 2 divided by 2, the log 5 divided by log 5. Simplify and reduce, and I'm left with the answer x equals 1 over 2 log 5. One last example, if we have something like 4 times 3 to the negative x power, all equal to 21. There's no obvious base to use, whether we use e or 10, whether we use the natural log or the common log. It's not exactly obvious because there's no e or power of 10 in the problem. So in this case, it doesn't really matter. We're going to start, however, by dividing both sides of our equation by 4. That's going to cancel out the 4 on the left side. And that leaves the exponential expression on the left side by itself. And 21/4 doesn't reduce, so we leave it 21/4. But by dividing 4 on both sides, that sets us up to be able to take the log of both sides. And like I said, the natural log of both sides or the common log of both sides will both work. In this case, there's no advantage to using one or the other. But you have to get the exponential by itself like we did by dividing both sides by 4 in order to then apply the rules of logarithms. The exponent negative x can come to the front. Negative x times the natural log of 3, and this is equal to the natural log of 21/4. We can get the x by itself on the left side by dividing by negative natural log of 3 both sides, negative natural log of 3. And that will leave us with x by itself, the natural log of 21/4 in the numerator, divided by the negative, or the opposite of the natural log of 3. If we wanted to expand that numerator a little bit to get a little bit of a nicer numerator, we can apply the quotient rule of logarithms and say this is the natural log of 21 minus the natural log of 4, all divided by the opposite of the natural log of 3. So that's a very nice looking exact answer. That's precisely correct, exactly correct. This is as well. And then if we wanted to get an approximate answer, we could plug this into the calculator. And the approximate answer is negative 1.509. And that's how we solve exponential equations, by applying the logarithm of both sides.